will give rise to the geometry that the physicists are finding beyond space-time. If we can do that, then we'd have a completely different way of looking at how consciousness is related to what we call the brain or the physical world more generally. Right now, all of my brilliant colleagues, 99% of them, are trying to. They're assuming space-time is fundamental. They're assuming that particles are fundamental, quarks, gluons, leptons, and so forth. Elements, atoms, and so forth are fundamental, and that therefore neurons and brains are part of objective reality. And that somehow when you get matter that's complicated enough, it will somehow generate conscious experiences by its functional properties. Or if you're panpsychist, maybe you, in addition to the physical properties of particles, you add a consciousness property as well. And then you combine these physical and conscious properties to get more complicated ones. But they're all doing it within space-time. All of the work that's being done on consciousness and its relationship to the brain is all assumed something that our best theories are telling us is doomed, space-time.
Why does that particular assumption bother you the most? So you bring up space-time. I mean, that's just one useful interface we've used for a long time. Surely there's other interfaces. Is space-time just the one of the big ones that to build up people's intuition about the fact that they do assume a lot of things strongly, or is it in fact a fundamental flaw in the way we see the world?
Well, everything else that we think we know are things in space-time.
Sure.
And so when you say space-time is doomed, this is a shot to the heart of the whole framework, the whole conceptual framework that we've had in science. Not to the scientific method, but to the fundamental ontology and also the fundamental methodology, the ontology of space-time and its contents, and the methodology of reductionism, which is that as we go to smaller scales in space-time, we will find more and more fundamental laws. And that's been very useful for the space and time for centuries, reductionism for centuries, but now we realize that that's over. Reductionism is in fact dead, as is space-time.
What exactly is reductionism? What is the process of reductionism that is different than some of the physicists that you mentioned that are trying to let go of the assumption of space-time, looking beyond? Isn't that still trying to come up with a simple model that explains this whole thing? Isn't it still reducing?
It's a wonderful question because it really helps to clarify two different notions, which is scientific explanation on the one hand, and a particular kind of scientific explanation on the other, which is the reductionist. So the reductionist explanation is saying, I will start with things that are smaller in space-time and therefore more fundamental, and where the laws are more fundamental. So we go to just smaller and smaller scales. Whereas in science more generally, we just say, like when Einstein did the special theory of relativity, he's saying, let me have a couple postulates. I will assume that the speed of light is universal for all observers in uniform motion, and that the laws of physics for uniform motion are those. That's not a reductionist. Those are saying, grant me these assumptions, I can build this entire concept of space-time out of it. It's not a reductionist thing. You're not going to smaller and smaller scales of space. You're coming up with these deep principles. Same thing with his theory of gravity, right? It's the falling elevator idea, right? So this is not a reductionist kind of thing. It's something different.
So simplification is a bigger thing than just reductionism.
Reductionism has been a particularly useful kind of scientific explanation, for example, in thermodynamics, right? Where the notion that we have of heat, some macroscopic thing like temperature and heat. It turns out that Boltzmann and others discovered, well, hey, if we go to smaller and smaller scales, we find these things called molecules or atoms, and if we think of them as bouncing around and having some kind of energy, then what we call heat is really can be reduced to that, and so that's a particularly useful kind of reduction, is a useful kind of scientific explanation that works within a range of scales within space-time. But we know now precisely where that has to stop, at 10 to the minus 33 centimeters and 10 to the minus 43 seconds. And I would be impressed if it was 10 to the minus 33 trillion centimeters. I'm not terribly impressed at 10 to the minus 33 centimeters.
I don't even know how to comprehend either of those numbers, frankly. Just a small aside, because I am a computer science person, I also find cellular automata beautiful.
Yes.
And so you have somebody like Stephen Wolfram, who recently has been very excitedly exploring a proposal for a data structure that could be the numbers that would make you a little bit happier in terms of scale, because they're very, 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 very tiny. So do you like this space of exploration, of really thinking, letting go of space-time, letting go of everything, and trying to think what kind of data structures could be underneath this whole mess?
That's right. So if they're thinking about these as outside of space-time, then that's what we have to do. That's what our best theories are telling us. You now have to think outside of space-time. Now, of course, I should back up and say, we know that Einstein surpassed Newton, right? But that doesn't mean that there's not good work to do at Newton. There's all sorts of Newtonian physics that takes us to the moon and so forth, and there's lots of good problems that we want to solve with Newtonian physics. The same thing will be true of space-time. We'll still, it's not like we're going to stop using space-time. We'll continue to do all sorts of good work there. But for those scientists who are really looking to go deeper, to actually find the next, just like what Einstein did to Newton, what are we going to do to Einstein? How do we get beyond Einstein and quantum theory to something deeper? Then we have to actually let go. And if we're going to do like this automata kind of approach, it's critical that it's not automata in space-time, it's automata prior to space-time, from which we're going to show how space-time emerges. If you're doing automata within space-time, well, that might be a fun model, but it's not the radical new step that we need.
Yeah, so the space-time emerges from that whatever system, and like you're saying, it's a dynamical system. Do we even have an understanding what dynamical means when we go beyond? When you start to think about dynamics, it could mean a lot of things. Even causality could mean a lot of things if we realize that everything is an interface.
Right.
How much do we really know is an interesting question. Because you brought up neurons, I got to ask you another tangent. There's a paper I remember a while ago looking at called Could a Neuroscientist Understand a Microprocessor? And I just enjoyed that thought experiment that they provided, which is it's a couple of neuroscientists, Eric Jonas and Conrad Cording, who use the tools of neuroscience to analyze a microprocessor, so a computer chip.
Now, if we lesion it here, what happens and so forth, and if you go and lesion in a computer, it's very, very clear that lesion experiments on computers are not going to give you a lot of insight into how it works.
And also the measurement devices and the kind of sort of just using the basic approaches of neuroscience, collecting the data, trying to intuit about the underlying function of it. And that helps you understand that our scientific exploration of concepts, depending on the field, are maybe in the very, very early stages. I wouldn't say it leads us astray. Perhaps it does sometimes, but it's not anywhere close to some fundamental mechanism that actually makes the thing work. I don't know if you can sort of comment on that in terms of using neuroscience to understand the human mind and neurons. Are we really far away potentially from understanding in the way we understand the transistors enough to be able to build a computer? So one thing about understanding is you can understand for fun. The other one is to understand so you could build things. And that's when you really have to understand.
Exactly. In fact, what got me into the field at MIT was work by David Marr on this very topic. So David Marr was a professor at MIT, but he'd done his PhD in neuroscience, studying just the architectures of the brain. But he realized that his work, it was on the cerebellum. He realized that his work, as rigorous as it was, left him unsatisfied because he didn't know what the cerebellum was for.
Yeah.
And why it had that architecture. And so he went to MIT and he was in the AI lab there. And he said he had this 3-level approach that really grabbed my attention. So I when I was an undergrad at UCLA, I read one of his papers in a class and said, who is this guy? Because he said you have to have a computational theory. What is being computed and why? An algorithm, how is it being computed? What are the precise algorithms? And then the hardware, how does